All right, we are in section 2.2, and we're looking at relations and functions, domain range, and then also some symmetries. So we're going to start out here with a set of points, and the set of points is a relation. And the start values, the input values, are the domain. So we list the domain values, and then the output values, sometimes the y values, that's the range that we're looking for. And we want to figure out whether this set of numbers is a function or not. Is this relation a function? And in this particular case, the answer is no. And we're going to rely on the vertical line test. So if we pass the vertical line through a couple sets of numbers, here it fails, right? It's because it's going to go through 2, 2 and 2, 3. That's more than 1 point in the vertical line test, and so for that reason it fails the vertical line test. It's a relation, not a function. It fails it again here, going through 1, -1 and 1, 1. It is not a function. Now we could change this relation by eliminating a couple of the points, and then it would be a function because it now satisfies the vertical line test. It's just any vertical line is going to go through just 1 point. So any input has a unique output. And so this set of numbers, a set of ordered pairs, it's a relation, and it's also a function. Now if we're looking for some symmetries, we want to see if if the set of points has mirror images, sets of mirror images with respect to the x-axis, y-axis, or the origin, and they don't. So it doesn't have any symmetry. All right, let's try the next problem, which is a very simple function, y equals 4. The domain is all reals. The output is just 4. And it is a function because any vertical line, wherever you draw the vertical line, will just cross through once. And so it passes the vertical line test. It is a function. This relation is a function. It doesn't have any x-axis symmetry because any point, if I reflect with respect to the x-axis, it doesn't appear on the curve. It does have y-axis symmetry because if I look at a point on the curve, like maybe 1, 4, and I reflect that to -1, 4 with respect to the y-axis, well, they're both on the curve, so it has y-axis symmetry. It's true for all points that are on this curve. No origin symmetry, though. Any point that I reflect with respect to the origin, that new point, reflected point, doesn't exist on the curve. Let's take a look at a parabola or a quadratic, and the domain is all reals. I can plug in any x value, any real number. The range is limited. It starts down at the bottom at -3.7 and goes up, but it satisfies the vertical line test, so it is a function. The answer is yes there, wherever I draw that vertical line. This particular quadratic or parabola does not have x-axis symmetry. It doesn't have y-axis symmetry. So again, you would take a point on the curve, and if you see that the reflected point with respect to the x-axis doesn't exist, then it's not x-axis symmetry. Same for y, same for origin symmetry. The answer is no for that. All right, next let's take a look at a circle. This circle has domain -3 to 3, range -3 to 3. It does not satisfy a vertical line test. Here this vertical line passes through 2 points. So the x input has 2 y outputs. It's not a function. It has all types of symmetry, though. It has x-axis symmetry. Any point on the curve, if you reflect with respect to the x-axis, it's also on the curve. Any point, if you reflect with respect to the y-axis, it's also on the curve. And even if you reflect a point with respect to the origin, that reflected point is also on the curve. So it's true for that circle. Let's try the next one. Next one is a curve that's called a hyperbola. The domain is any real x. The range, I don't get any y values from -2 to 2. It is not a function because it does not pass a vertical line test. So drawing a vertical line there, in any spot, you're going to find that it crosses through 2 points. And it has all types of symmetry. It has mirror image with respect to the x-axis, mirror image with respect to the y-axis. And if you take any point and you reflect it with respect to the origin, that point is also on the curve. Okay, next, let's take a look at a trig function. So this is a cosine curve, and the range is from -2 to 2. It is a function. You can see that it satisfies the vertical line test. It doesn't have x-axis symmetry because if we take a look at a mirror image with respect to any point on the curve, That new reflected point doesn't exist on the curve. It does have y-axis symmetry though. Any point on the curve, you reflect it with respect to the y-axis. That reflected point is also on the curve. No origin symmetry. So take a point, reflect it with respect to the origin. It's not on curve. All right, next we have another parabola. This parabola is kind of lying on its side in relation to how we typically expect to see parabolas. It is not a function because it does not satisfy a vertical line test. See, you can see that it crosses through twice here, more than once. Fails the vertical line test. It does have x-axis symmetry. It's a mirror image with respect to the y-axis. No y-axis symmetry and no origin symmetry for this curve. Next, we have a very simple function, y equals 1 over x. It is a function. As we see, it satisfies the vertical line test. You can't plug in 0 because we can't divide by 0. But on its domain, it is a function. It does not have x-axis symmetry. It doesn't have y-axis symmetry. It does have origin symmetry, though. So if you take a point on the curve and you reflect that with respect to the origin, you kind of pass it through the origin, look on the other side, that point will exist on the curve. We also have a piecewise defined function made up of some line segments. Again, this is a function satisfying the vertical line test. This particular piecewise defined function doesn't have any symmetries. No x-axis, no y-axis, and no origin symmetry in this case. So you might try to reflect the points and see if they exist, and they don't. Last example is another polynomial, and this polynomial is a cubic, and this cubic is a function, and we'll talk more about polynomials in general later, but it satisfies the vertical line test, and this particular cubic doesn't have any x-axis, y-axis, or origin symmetries. Now let's try some problems where we write them out, and these come from our example problems. And we've got a function x over x plus 1, and we want to know if this given point is on the graph. So let's plug in the x value of 1, and we get 1 over 2. And what do you know? That is the given point, 1, 1/2. It's on the graph of the function. What is the function at 2? Well, let's plug in 2 for x and see what we get. 2 over 2 plus 1 is 2/3. And so 2 2/3 is on the graph of the function. Where is the function equal to 2? Well, set the function equal to 2, and then you can multiply and solve for x. You get x equals -2. That would mean that the point -2, 2 is on the function. We'll plot these points toward the end of this video just to see that they are on the graph. What is the domain? Well, if we were looking for the domain, we want to make sure that the denominator is not 0. So we can't have x equals -1. We toss that out. We should be able to write that either with our interval notation or in our set builder notation. So either one. If we're looking for x-intercepts, we want to set the function or the y value to 0 and just solve. So 0 equals the function, x over x plus 1. And that would mean the numerator has to be 0, and that's x equals 0. So that means 0, 0 is the x-intercept. For y-intercepts, it's not y equals 0, you set x equal to 0. So just plug in x equals 0, and we get 0. And so the y-intercept is at 0, 0, which is the origin, and the x and y-intercept is the same because it is the origin. And we'll plot these points toward the end again of this video. Let's try a word problem. So in this word problem, we've got a Boeing 747. And if we plug in the ground speed, we can get the cost in dollars. So ground speed, the input is in miles per hour, cost is in dollars. So we're going to plug in a couple specific values, 200 for x, and we get 1,000 plus 2 plus 18. That's $1,020 if the ground speed is 200 miles per hour. And then if we speed things up, plug in 350 for x, divide, and we have to do an approximation here because the 3,600 by 350 isn't going to come out as an integer. And we come up with a decimal approximation and then do some addition, and we get 1,013.7857. It looks like the cost has decreased a little bit when we go from 200 miles per hour to 350 miles per hour. So keep that in mind. If we're looking at the domain, we want to think of what's reasonable for the ground speed. So I don't think we want to use a ground speed of 0, and we also probably want to make sure that it's not negative. So we might start with a domain of 0 to infinity, and we could even talk about that infinity. What's a reasonable maximum for a plane, a ground speed? So it might be something less, but we might start with 0 to infinity. All right, the last two problems of this this sample problem ask us to use a graphing utility. So we can just type in the cost function into our graphing calculator or Desmos. I'm using Desmos here and plugging it in. And it doesn't look too good there to start. So you might hit the wrench icon, and we've plotted a couple points with part A. So you have kind of you know what the reasonable values are. So we can maybe set the x-axis and y-axis to some reasonable limits and then plug in, and then you can get a better sense of what that's going to look like. And in the next part, it asks where is the cost minimized. So you can hit the little gear icon and then the table icon, and then just plug in some values. And if you use some values that are the same step away, you can just start hitting the enter key and it'll fill it in. And now it looks like the minimum is going to be somewhere in the middle of that domain that we have there. We can maybe zoom in a little bit, and it looks like the minimum is at 600, a ground speed of 600 miles per hour. And you can see that both in the graph and in the table. So the minimum is when the ground speed is 600. You can zoom in and out to get kind of a better sense of what it looks like. But we've answered C and D there for the problem. And if you zoom in a little further, I also said we go back and take a look at the function x over x plus 1. So don't have to zoom much for that. And we've plotted some points. If you go back and look at this problem, we found some points in parts A, B, C, and then I think F. And they were negative 2, 2, and 0, 0. Those were our intercepts, 1, 1/2, and 2, 2/3. And what do you know? All three of those are actually on the graph of the function. And that wraps things up for us.